All right, in this video, I'm going to cover techniques of estimation. Let's start with the concept of point and confidence interval estimates. Imagine that we take a random sample from a larger population, and we don't know the mean of the population, so the sample helps us understand this. Let's imagine that the mean of the sample, x bar, is 50. Well, a point estimate would be just that. It would be 50. We would assume that the population mean is 50 because our sample mean is 50. However, that's not the common way of using inferential statistics. What is common is a confidence interval estimate, which is a range of numbers. First, we establish a confidence level, which we'll assume is 95%. Sometimes this is stated as 1 minus alpha, where alpha would be the area outside of your tails in a bell curve. For example, here, if we have a distribution that's normal, okay, and let's say we want a 95% confidence interval, well, this would be the 95% confidence interval, which would leave alpha 5% in the tails. That means each tail would have alpha divided by 2. That is, 5% divided by 2 would be 2.5% in this tail, and then 5% divided by 2 would be 2.5% in this tail, again leaving 95% in between. Remember, the whole area under the bell curve must sum to 100. So once you establish that this area here is 95%, 1 minus 5%, then you automatically establish what these areas are. So what this will allow us to do is set the confidence level and then find the range of values that this 95% here interval represents. For example, if we take the sample from a larger population and we get a mean of 50, we might be able to say that we're 95% confident that the true population mean is between 40 and 60. This is the more common way of communicating inferential statistics. If I, for example, go and collect a sample of San Diego State students, let's say I select 100 students randomly from the school, and there's 30,000 students in the whole school, then I'm going to get a point estimate. Let's say I get 3.0 as the average grade for my point estimate. But that doesn't mean that the average student at San Diego State has a 3.0. That just happened to be the mean of my sample. But that will give me information, because what I may be able to do is determine, based on that 3.0 mean for my sample, maybe the true population grade point average is between 2.5 and 3.5. In other words, I can create this interval that will give me a sense of where that true population mean lays. Not exactly what it is, but a range of values that it's likely to occupy. And I can create that range with a certain level of confidence. So I might be able to say that I'm 95% confident that the true population grade point average is between 2.5 and 3.5 simply by selecting a sample. Okay, keep that in mind as we progress, because it is tempting to consider the mean of the sample as representing the true population mean. It doesn't. It's just a starting point for creating that confidence interval to help us get to where that population mean likely is. Take a look at this bell curve down here again. You'll notice that we've got x bar on our axis, which means this is actually a confidence interval that we saw in the last lecture video. It is an interval illustrating the mean of sample means. In other words, if you took every possible sample from a particular population, then you would expect the mean of each of those samples to have a distribution that is normal, and the mean of the sample means would equal the mean of the population. More specifically, we can use this diagram to highlight a 95% confidence interval. Now, we're starting with 95, but of course we could do other intervals as well. So what we would have is, from before, 1 minus 5%. The values from this point here to this point here would be 95% of the data. That means that 95% of our sample means, of all the means that are possible, 95% would lie in this range here. And then on occasion, 5% of the time, you would get a sample mean that's over here, or you would get a sample mean that's over here. In effect, 2.5% of the time, you would get a sample mean that would be up here, and 2.5% of the time, you get a sample mean that's down here. Let's refer back to our grade point average example. If I've got 30,000 students at San Diego State, and I were to take every possible sample of 100 from San Diego State, that would be a lot of samples, and each one of them would have a unique sample mean, and I would illustrate the distribution of those sample means here. Now, let's say that the mean of the sample means is 3.0. Well, that would be our population mean as well. But what's interesting is if I were to select any particular sample, I'm probably going to get a value above that or below that. Let's do that. Let's say I take one of those samples and I get this value here. Well, that's above our mean here of sample means. So if the mean of sample means is 3.0, let's say I pull this sample happens to be a 3.3. And then I take another sample of 100 out of 30,000 and I get maybe a 2.8. Then I take another sample, 100 out of 30,000, and I get a 2.7. Then I take another sample, I get 3.1. I take another sample, I get 3.05 or something like that. You'll notice that most of the time, my sample means are going to be proximate, pretty close to the mean of sample means. It's a normal distribution. Most of your data is going to lie in this interval here. It's going to lie pretty close to the mean. But on occasion, I will get a sample mean that isn't close. Maybe it's way down here. Maybe I get a sample mean that's down here in this tail, 1.0. That's going to happen, but not very often. Similarly, what if I get a sample mean way up here at 3.9? That's going to happen, but not very often. Once I have a particular sample, I can then get a sense of what the population mean actually looks like. The sample mean here, for example, is based on my data that I collected in this sample. Say the n equals 100 out of 30,000 in the population. The mean is here, let's say 3.3, and now I just construct a 95% confidence interval around this mean. You'll notice that that's represented by the bar here. So 95% of my sample data lies between this sample mean and here and here. Note that the population mean is part of that 95% confidence interval. What if I get this sample mean? Let's say it's 2.8. Well, again, I find a 95% confidence interval around that sample mean, get data all the way down to here and up to here, and notice the population mean is in that interval too. Then I select another sample and I get a mean here, construct a 95% confidence interval, and the sample mean is in there, and I keep going. And most of my sample means are going to have a 95% confidence interval that includes the true population mean, which implies that I can go out and select 100 students out of 30,000 in the school. That will give me a sample mean. I can then look at the distribution of that sample mean, create a 95% confidence interval around that sample mean, and be 95% confident that the true population mean lies within that range. And more often than not, I'll be right. Another way to think about this is with the actual mathematical intervals. Now, we're going to practice this in a bit, but I just want to give you a flavor for it now. A lower confidence level is the lower level here that we would get from our sample. The upper confidence level is the upper level here that we would get from the sample. So the lower confidence level, for example, would be our X bar, and we would subtract a Z-score based on a 95% confidence interval multiplied by this value here. Now, if you recall, that is our standard error. Okay? When you take a Z-score and you multiply it by a standard error, you get what's called the margin of error. So what we've done to construct this lower confidence level from this sample is we've taken the mean and subtracted a margin of error. That's the lower bound in which our true population mean could lie based on that sample. The upper confidence level would be the sample mean plus the margin of error. That would be the upper bound in which that true population mean could lie. So we're creating bounds, a lower confidence level and an upper confidence level, telling us where that true population mean likely lies. But it's all based on a sample. And this is inferential statistics. We go out, we collect a sample and get the mean. We create a 95% confidence level interval with lower and upper bounds to establish the range in which that population mean lies. And we do that based on the z-tables. Okay, let's move on. In the event we're looking at a population where the standard deviation of that population is known, that is, we know how the data in the population is distributed, then we can estimate the mean with this formula here. It's simply our sample mean plus and minus the z value times the standard error, which is the same as the sample mean plus or minus the margin of error. This is the same as creating those endpoints I talked about a minute ago. The lower confidence level being the lower endpoint and the upper confidence level being the upper point. One thing we like to do when estimating a population mean is try to minimize this margin of error. Because think about it, the smaller the margin of error, the closer our population mean is going to be to our sample mean. And there's three ways to reduce your margin of error. And you can see this in the actual formula here. For example, one way is if the population standard deviation is reduced, that is, if alpha is lowered, then our standard error is lowered, which reduces our margin of error. So if we know, for example, that the population has less variation in its data, then that's going to give us a lower margin of error when we estimate that population mean than otherwise. If we increase the sample size, that will also lower our margin of error. Our sample size is in our denominator here of our standard error formula. So if the denominator goes up, then the standard error goes down, and that lowers our margin of error. Okay? Makes sense there. Bigger sample size, less margin of error, more likely to get a estimate that is closer to the true population mean, a sample mean that is closer to the true population mean. And think about it on an extreme basis. If n goes all the way up to the population, then effectively you've eliminated your margin of error. The third way is the confidence level is decreased. If we lower our confidence level, we're going to see this in our z-table, then we'll actually be able to lower our z-score and effectively lower our margin of error. Okay, we'll pick up from here in the next video. Thanks.